Hello and good day, learners. I am Kea Sacapaño, and for this lesson, we will be learning about repetition and the Hamming distance. So for the repetition code, we might use this repeating method to encrypt the message 01101, which would result in the characters 000111111000111. So in this instant, you may notice that each bit was repeated 3 times. And we may correct a random bit flip or error by simply taking the most frequent bit out of each 3-bit segment. So let us take this message for example. We have the message after source encoding, which is 11100100. So the given is r is equal to 3, which means that this will be repeated 3 times. So your channel encoding will then be x sub 1 and x sub 2, which will then be repeated 3 times. So for the first one, we have our x sub 1 and x sub 2 as 1, 1. So this will then be encoded to 1, 1, 1, 1, 1, 1. So as you can see, the ones were repeated 3 times. For the next one, we have our x sub 1 and x sub 2 as 1, 0, which would then again be repeated 3 times, 3 ones and 3 zeros. So applying the same repetition to the next bits will give you 000111 for 01 and 000000 for 00. So the same method was also applied to this next example where your r is still equal to 3. So take note that each bit string is repeated 3 times. So for the next example, we have Bella sent her message Y using repetition code r is equal to 5. So they received the binary word r is equal to 11111, 10101, and 00010. So is there an error in the transmission? The answer is yes. And this is because Dave was supposed to receive a binary word with a repetition code of 5. But as we can see in the message that he's received, there was only 1 bit that was repeated 5 times. So according to the majority decoding process, for each block of 5 binary digits, the original bit must be the one that appears more frequently in the block. For example, let's take the received word r is equal to 11111, 10101, and 00010. It must be corrected. So this will be the corrected block. We have the first block to remain the same as it is already following the repetition code. We have the next one, 10101. All the zeros will be replaced by ones in order for it to be a repetition code of 5. For the last one, we have 00010, wherein 1 will be replaced by 0. For it to have a repetition code of 5, your y will then be equal to the corrected repetition code of 11111, 11111, 00000. So the problem with the prior example is that there is no practical way to fix the error that was made. The reason for this may be seen in the graph below, where each node represents one of the 3 possible combinations of 3 bits. Bold font indicates valid code words or those whose parity bits are accurate. Then, for each edge, a bit flip corresponding to the connected nodes will be represented. By moving along 2 edges or making 2 bit flips, we can move from one valid code word to another if we start at any one of them. These traversals can be thought of as the Hamming distance, which is the distance between code words. So the Hamming code encodes 4 bits to 7 bits, hence the name H74. So the messages take the form x sub 1, x sub 2, x sub 3, x sub 4 to x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, x sub 6, and x sub 7. And messages have 4 binary digits, which is the total of 16 messages. Each code word is a length of 7, wherein you add 3 redundancy digits to form the code word. So for example, we have our channel encoding of x sub 1, x sub 2, x sub 3, and x sub 4, and add 3 redundancy digits to form the code word, which is why we add x sub 5, x sub 6, and x sub 7. So this is the formula for x sub 5, x sub 6, and x sub 7. So let's take this message for example. We have our x sub 1, x sub 2, x sub 3, and x sub 4 as 0110. So to get the x sub 5, again we have x sub 1 plus x sub 2 plus x sub 4, which is 0 plus 1 plus 0, which is equal to 0. This is equal to 0 because we only have 1, 1, which is an odd number. Next, for the x sub 6, we have x sub 1 plus x sub 3 and x sub 4. So we have 0 plus 1 plus 0, which is also equal to 0 since we only have 1, 1, which is an odd number. And lastly, we have x sub 7, which is equal to x sub 2 plus x sub 3 plus x sub 4. So we have 1 plus 1 plus 0, which is also equal to 1 since 1 plus 1 is equal to 2 and 2 is an even number. We will then complete the code word from x sub 1 to x sub 7, which is equal to 0110001. Now for the Hamming distance. So the Hamming distance d of xy between the bit string x and y is the number of positions to which these strings differ. For instance, the Hamming distance between 110 and 000 is 2. We can see that there is no way to tell which of the correct codes was transmitted by starting with an invalid code that contains an error, as the invalid code is one of 3 valid codes. This suggests that all 3 options would be equally likely. The minimal Hamming distance between any 2 valid code words is the same as the Hamming distance of an entire code. For example, for A we have D of 00110 and 10101 to have the Hamming distance which is equal to 3. This is because the Hamming distance between these 2 codes are 1, 2, and 3. So you will then get the Hamming distance of 3. So for letter B, we have D of 11101 and 00011, which is equal to the Hamming distance of 4, because we have 1, 2, 3, and 4 differences, which is equal to the Hamming distance of 4. For letter C, we have D of 12234 and 22334, which is equal to 2, since we have 1 and 2 differences, which is equal to the Hamming distance of 2. For another example, we have let C be equal to 11111, 11101, 01011, and 00100. Suppose that the string 01110 is received. So we will compare the received string of 01110 from the previous strings. First we have D of 01110 and 11111, which is equal to the Hamming distance of 2, since they differ in 2-bit strings. Next, we have D of 0110 and 11101, which has the Hamming distance of 3, since they differ in 3-bit strings. Now we apply the same method for the next bit strings, and we should be able to get the Hamming distances of 3 and 4 for it. So the closest code word to the received string is 11111, with the Hamming distance of 2. Hence, the receiver assumes that this was the original string. So take note that the number of errors that can be detected and corrected depends on the Hamming distance between the code words. So we have the theorem where we let C be a set of code words and let 2E plus 1 be the minimum Hamming distance between any code words in C. Then, it is possible to detect up to 2E errors, and it is also possible to correct up to E errors.